The most distant black hole ever detected is located in a galaxy about 13.1 billion light-years from Earth. The age of the universe is currently estimated to be about 13.8 billion years, so this means this black hole existed about 690 million years after the Big Bang. This supermassive black hole is what astronomers call a quasar, where large quantities of gas are pouring into the black hole so rapidly that the energy output is 1,000 times greater than that of the galaxy itself. Its extreme brightness is how astronomers can detect it at such great distances. The universe is a big place. In particular, the size of a region where a particular black hole has significant gravitational influence is quite limited compared to the size of a galaxy. This applies even to supermassive black holes like the one found in the middle of the Milky Way. This black hole has probably already eaten most or all of the stars that formed nearby, and stars further out are mostly safe from being pulled in. Since this black hole already weighs a few million times the mass of the Sun, there will only be small increases in its mass if it swallows a few more Sun-like stars. There is no danger of the Earth, located 26,000 light-years away from the Milky Way's black hole, being pulled in. Future galaxy collisions will cause black holes to grow in size, for example by merging of two black holes. But collisions won't happen indefinitely because the universe is big and because it's expanding, and so it's very unlikely that any sort of black hole runaway effect will occur. Yes. The late physicist Stephen Hawking proposed that while black holes get bigger by eating material, they also slowly shrink because they are losing tiny amounts of energy called Hawking radiation. Hawking radiation occurs because empty space, or the vacuum, is not really empty. It is actually a sea of particles continually popping into and out of existence. Hawking showed that if a pair of such particles is created near a black hole, there is a chance that one of them will be pulled into the black hole before it is destroyed. In this event, its partner will escape into space. The energy for this comes from the black hole, so the black hole slowly loses energy and mass by this process. Eventually, in theory, black holes will evaporate through Hawking radiation. But it would take much longer than the entire age of the universe for most black holes we know about to significantly evaporate. Black holes, even the ones around a few times the mass of the Sun, will be around for a really, really long time. The nearest black hole to Earth is V616M Monocerotis, also known as V616 Mon. It is about 3,000 light-years away and has a mass 9 to 13 times that of our Sun. We can only infer its presence by the fact that it is located in a binary system with a star buzzing around it. Quickly. Low-mass black holes could be formed on Earth only if the matter was compressed to enormous densities by very high external pressure similar to a huge hydrogen bomb. If one took all the heavy water in all the oceans of the world, one could build a hydrogen bomb that would compress matter at the center so much that a black hole would be created. Of course, no one would be left to observe it. To a distant observer, time near a black hole would appear to pass more slowly than those further away from the black hole. Due to time dilation, an object falling into a black hole seems to slow as it approaches the event horizon, taking an infinite time to reach it. Black holes are predicted to emit radiation known as Hawking radiation, the name given after Stephen Hawking Ng. It is speculated to be released due to quantum effects near the event horizon. According to Albert Einstein's theory of general relativity, black holes are uninhabitable chasms of space-time that end in a singularity, or a mass of infinite density. But a new theory based on loop quantum gravity, LQG, suggests that black holes might not culminate in a singularity. It proposes that space-time is granular and is made up of indivisible chunks about the same length as the Planck length, which roughly amounts to 10 raised to 35 meters in size. Researchers crunched the numbers to see what would happen inside a black hole on the parameters of LQG. What they found was contradictory to the theory of relativity. There was no singularity. Instead, just as the black hole began to squeeze tight, it suddenly loosened its grip again, as if a door was being opened. Theoretically, black holes might be portals to other universes.